One of the biggest obstacles in implementing renewable energy is actually storing the energy that is produced. We're a group of freshmen at Drexel University in Philadelphia working on a new energy storage technology to address this specific need. We call it an electrochemical flow capacitor, or an EFC for short.
It operates by pumping carbon particles and an electrolyte through a cell. Each cell is composed of two conductive plates with a separator in the middle. When a charge is applied to the cell, anions in the electrolyte are attracted to the positively charged plate, while cations are attracted to the negatively charged electrode. We can then separate this charge and store it into two separate tanks. When we want the energy back, we discharge the system by pumping the charged carbon material back through the cell. This design has several advantages. Since EFCs store energy through physical electrostatic interactions with no chemical reactions, they could potentially withstand a few million charge and discharge cycles. EFCs also use abundant and low-cost materials like carbon particles to store energy. And since it's a flowable electrode, EFCs can be scaled to any size application. You just need big enough tanks.
The most unique feature of this device, which we call electrochemical flow capacitor, is that we can store energy in tanks, which hopefully will be very large tanks, allowing us to store more energy. You just cannot have many small batteries like the one we use, say, in our cell phones or computers, pack rooms or buildings with those here. We want to be able to store energy in an inexpensive way, and flowable system, when there is a big tank with a media storing it, is clearly the least expensive solution.
We wanted to build an EFC and demonstrate its potential. Our idea was to build a solar-powered system that uses an EFC to store energy and illuminate an LED. We began by creating a 3D computer-aided design model. Then, using mills, bandsaws, and laser cutters in Drexel's machine shop, we recreated the cell's components. The EFC uses abundant, cost-effective materials like polyethylene for the casing, graphite for the current collectors, and latex for the gaskets.
We assembled the cell and then prepared the slurry electrode. After pumping the slurry throughout the cell, we hooked up electrodes to the EFC and characterized its electrochemical performance.
We charge the EFC with a solar panel. When we want to use the energy, we simply press a button on the circuit which discharges the flow capacitor into the LED.
As a group of freshmen, it was exciting to work on such a huge problem and demonstrate technology that has the potential to address this issue.
I am from the Southern African country of Zimbabwe, and the widespread power shortages that we have can be attributed to insufficient power supply and a lack of grid energy storage facilities. From a global perspective, this is an exciting solution, and that I feel that should be investigated further in order to realize its true potential.
I believe that localized energy generation from solar batteries, wind power generators, other sources will become very, very common. Every home, every building will have some energy generation system that we can produce renewable energy.